Okay, good morning, everyone. So let's do a little bit of review because we haven't met in a while, right?
Yeah.
So the last time we finally stated the postulates of quantum mechanics. So the way to think about this for now is, here are some rules. I'm not going to tell you why these rules, how people came up with these rules, but these are the rules. Okay, and we're going to have a bit more of kind of these are the rules, and then eventually we will do some computations and kind of see how things kind of work, right? And play around with these rules. And actually today is going to be our first example with these rules. There's probably some way where you can kind of look at certain famous experiments that were done in the early 20th century and try and figure out, like from this experiment we can see that you have this rule. From this experiment you see that you kind of get that rule. But the problem is, I think there would be rather very many of these experiments that you'd need to discuss, and each one of them would take a while. And also, like Bohr wrote his stuff on the Bohr-Rutherford model. That was like the early 1910s, right? And then the rules written in this way, I think were written down maybe either in the late 1920s or the early 1930s by von Neumann. It's like a 20-year gap. And so, that means, I'm not familiar with this, but I feel like you would kind of have to explain the logic over a 20-year gap, and that would just take a lot of time. Okay. So rules, the postulates of quantum mechanics. We had a few of them. So let's review them. Okay, what was the first one roughly? Do people remember? First postulates of quantum mechanics? Yeah, let's just say it.
Never mind. I don't know the order.
Okay.
Is it like a state vector?
Yeah. Okay. What about
In a
it?
Hilbert space?
Yeah. So the state of a system. State of system described by some vector in some Hilbert space. So a Hilbert space is what? It's a complete inner product space. Inner product space. Do people know what complete means?
Yeah.
No? Okay. Do people know what a Cauchy sequence is? Okay.
Yes.
You can imagine that you can have a Cauchy sequence which doesn't converge to anything. Yes? Think of, for example, the real line, but then you remove the origin. Do you agree? And then you can have 1 over n, right? That's going to be a Cauchy sequence, but it's not going to converge to anything inside of my space, right? The points are going to get closer, but it doesn't converge to anything. Okay. So a complete inner product space is where this doesn't happen, where every Cauchy sequence converges to something in that same space. Okay, that's it. So actually, this is one of the points that in last year's videos I make a completely wrong statement about it. And actually, there was recently a paper, like last year or 2 years ago, arguing that this postulate isn't entirely physical. Like they cook up some particular special case where assuming this gives you something very strange that doesn't make any physical sense. But I have yet to sit down and read this paper in any amount of detail and make a smarter comment. But okay. The inner product space part is the one that we'll mostly talk about. Okay, state of the system described. Postulate number 2. So I told you something about the state of a system. So now I need to tell you, if I knew the state of a system, how would I do what? Measure anything, right? And so the next, I think, 2 and 3, or however you number them, talk about like measurement.
Like a metric?
What do you mean by metric?
Nothing, just sorry.
Okay. So a physical measurement actually, let me just do this. Okay. Physical measurement has an associated self-adjoint operator on this Hilbert space. Okay, and what? So first thing, well, I don't know. First thing, the eigenvalues of A tell me what?
The possible results of the measurements.
Yes, are possible outcomes of measurement. Okay, so if I have an observable and I want to know, in principle, what could I possibly ever measure in the system, like ever, right? Regardless of what state I'm in, for anything, to find out what could be measured, you compute the eigenvalues of this self-adjoint operator. Okay. Good. Part B is good. Now, so this kind of tells you, what could be measured regardless of what state I'm in, right? But surely the state the system is in should affect, what can be measured about the system and the state. And so, what do we, how can we figure out, what will happen? And so, suppose the system is in state psi, right? Some vector in the Hilbert space. Then the probability, probability to measure lambda. So remember, lambda is a possible outcome of my measurement. So it's some eigenvalue of a degree. So the probability to measure lambda if I'm in state psi is given by the inner product of what? Of psi. Sorry, the absolute value of the inner product, but the inner product of psi with psi projected onto the eigenspace of A with eigenvalue lambda.
Wait, is it?
Okay. Do people remember what a projector is?
Yeah.
Yes? Okay. So let's maybe make a separate side comment actually about what a projector is. Let me think about this. So like so P is the projector.
Oh, okay.
Projector onto the eigenspace, eigenspace with eigenvalue lambda of observable A. Okay.
And then you dot product it with itself.
Yes, and I dot product it with itself. So roughly speaking, how I can think of this, right, is suppose I write my state as some linear combination A1 of, okay, some eigenvector with eigenvalue lambda 1 plus A2 eigenvector with eigenvalue lambda 2 plus, okay, let's say something like this. Okay, then what P does it sends an eigenvector in the it takes a vector in the subspace and then sends it to itself, and then everything that's outside of the subspace it sends to 0, roughly. But you kind of have to be careful with this because this actually, yeah, that's what I will say. But yeah. The thing is, if you have a subspace, it doesn't necessarily define a projector onto it, because you could always write something as a strange linear combination, and then things would start depending on the choice of basis. But if you use you can use orthogonality to define a projector given a subspace. But okay, I don't want to talk about that too much. The point is the point being that as far as you're concerned, if you have an orthonormal basis, right? If I have an orthonormal basis, so these two are say orthogonal to each other, then P onto the eigenspace A of lambda applied to psi, say lambda 2, would just give me A2 lambda 2. Okay? So, and you can think of this projector thing, once again, this is very intuitive as to what this does. In R2, say I had some vector and I wanted to project it onto E1. Do you agree? So I project it onto this subspace. Okay, but that would just be the x component of the vector. Do you agree? And so it's going to take this vector and send it to this one. Right? And that's really what I wrote down here. Right? If I project onto the lambda 2 subspace, I'll just get this vector, and I just remove the part that has lambda 1 on it. Okay? Roughly makes sense? So actually, can someone tell me how this thing would look like? Actually, I don't even need this square here. I can just leave it like this. I believe. Yeah, that's right. Someone told me if this was my state and I was got lambda 2, what would this be equal to? If this was my state and I measured lambda 2, what would my probability be to measure lambda 2?
Notation question. That's not the P in the dot product.
No, that's the same one.
The same P. Okay.
So I'm telling you, if this was the state, and I had lambda 2, then what do I get?
50%. 50,
I mean,
you get the
not
second
quite.
half.
I'm asking you to compute what am I asking? I'm asking you compute this. Do you agree?
Yeah.
Where psi is this,
yeah.
and the other one is this. Okay.
Just
And lambda 1 and lambda 2, I assume that this notation. Maybe I should have said
A2
this.
squared.
This is just a vector. This is like some vector, and this is some vector.
A2 squared.
A2 absolute value squared.
Okay.
Okay. Do you agree?
Wait.
Do you see why that's the case?
Orthogonal.
Yes, assume lambda 1 and lambda
Okay.
2 are orthogonal vectors.
Mhm.
Okay, sorry. I'm not being clear. I didn't say what lambda 1 and lambda 2 are. Remember, our observable A is self-adjoint. Do you agree? So it has a spectral field. Do you agree? So there's a basis of eigenvectors.
Mhm.
Do you agree? So I can label, okay, in a certain case, I can label my eigenvectors by their eigenvalue. Do you agree? So suppose this is the eigenvector of A with eigenvalue lambda 1, and this is the eigenvector of A with eigenvalue lambda 2. Okay, this is the notation I have. Okay, so that's fine. So maybe maybe one way to write this is is A psi lambda squared lambda, yeah, psi lambda is in the eigensubspace of A with eigenvalue lambda. Okay? So this is another way to write this, is to kind of say I write down my vector in my basis of on my orthonormal basis of eigenvectors, and then I look at the components squared in front of the vectors that have the eigenvalue I'm interested in. Okay? Don't worry, we'll look at a few examples, and I think you should have looked at an example at the end of last session, right? You had like this a switch turned on, switch turned off example, right? And then you looked at some probabilities that are associated with it. Okay, maybe you did, maybe you didn't. That's okay. Okay, so right, and then right, and then I had part C is if system is in a state psi and lambda is measured in the lab, is, well, not measured, is observed in lab, then state collapses to psi goes to the projection to the eigensubspace A lambda applied to psi divided by its own length. Yeah. Okay, yeah, see you. Or, yeah, that's a good. It's good.
Equal to.
So, does this notation make sense? I just want to, when I write dot like this, I mean divided by, the length of the thing that's above. I just don't want to write the same thing twice. Okay. Right, and then we had D, which was Schrodinger equation. No, not D, but 1, 2, postulate 3, which was Schrodinger equation. Did you state the Schrodinger equation? Okay. I don't want to do it right now. It's well, actually, Schrodinger. You know what? Let's write it down. Anyway, I don't think people can even see it here, but it is what it is. IH bar partial t. I'm gonna mess up the minus sign, but that's okay. IH bar partial t of psi is equal to h applied to psi. Is that right? Or do I have a minus here? I think I have a minus here. Or other way around. Something like this. You have some equation which tells you how the state should evolve in time. Okay? Okay. Good. I recently found out that this tea gets its flavor because there's some bug that bites the shrubs of the tea and leaves some acid or something on it, and that contributes to the flavor.
That's not
I
too
did
bad.
not know this when I purchased the tea, but I know this is I like it.
That's not too bad. Do you know the red lipstick has bug husks in it?
Oh, that's probably true.
Well, yeah, the red.
Red cochineal beetles on cactus plants. Red 40.
That's
not
probably-
red 40.
Yes. Okay. So we did a quick recap. Now let's do a recap of the recap. Okay, question.
Sorry, could you repeat what the notation in 3
This
means?
in this one,
Yeah.
this just means write this in here again, and I'm too lazy to
Okay.
write the
I
same
see.
thing twice.
Thank you.
The amount of time I've spent explaining, I might as well just write it down.
But this is the P that we use for the projection, not the.
This is the
okay.
projection. Yeah.
Okay.
Was there any other P? Oh,
There's-
yes, sorry.
what is that?
This is the probability of measuring lambda.
Okay.
Actually, this should maybe have a psi subscript. Maybe it should be
Yes.
the probability of measuring lambda if I'm in state psi. Okay? And this is the projector onto the eigensubspace with eigenvalue lambda,
Mhm.
eigensubspace of A
Okay.
with eigenvalue. Okay?
Oh. Okay. Yes.
Yes.
That makes all more sense.
Much
Yes.
more clear thing.
Okay. So let's see. What does this all mean? Okay. Let's kind of do a bit of a recap of the recap. So okay, I'll give you a moment to finish writing. Yeah. And then we'll look at an example. Finally, we'll solve. Well, no. No. First, we'll have more rules that are arbitrary, but they work, and then we'll do an example.
Lovely.
Wait, am I next week?
Huh?
Am I next week?
Yeah. Don't worry, it's fine. You're in good hands.
It's actually over for me, bro.
Do you have a midterm next week?
We have
I have a
two.
midterm.
Oh,
two
you have one.
final
Yeah.
projects, basically.
Okay, we'll meet. Are they
Applications.
due on Friday? Is anything due on Friday?
You don't.
Everything's due on Thursday.
Perfect. You'll present on Friday.
Okay.
And if you want, you can meet with the person like
so I just
Friday
meet
morning.
right before and then just like. do it.
Well, you should meet like a bunch before, but you know, you can. That's fine. You'll try. You'll get things wrong, and then I'll correct you, and that's okay. Good. So let's recap.
Okay.
The state of the system is described by some vector in some Hilbert space.
Mhm.
Whatever this Hilbert space is, we don't know. But okay. Then I want to be able to measure something, and with every like measurement that I can physically do in the lab, there is some self-adjoint operator that's associated to it. When I say associated, I mean kind of in some loose sense. Yes.
What is self-adjoint?
Self-adjoint. Remember, an operator was self-adjoint if U inner product V was equal to
A star.
V for all U and V.
Oh, like
If it's an adjoint of itself.
Oh, I see.
Oh,
Okay.
okay.
Remember? And then we had a spectral theorem for self-adjoint operators. Yes? You remember what the spectral theorem was?
Was this last week?
No, this was the week before that. This was like
Oh,
the
you
one
did-
week
I
that
did
like
know
everyone
at some
skipped.
point. Oh wait, then.
This was the one week that like everyone skipped, and Alisher just gave a presentation to like me and maybe one other person, I forget.
Thank you.
Yes. So, and then I told you like multiple times that you really need to know what the spectral theorem is. People remember? Okay, statement of the spectral theorem.
I'll tell you next time I have to.
No, right now. Because I mean, this is also in 247, so you should know this probably by now.
I don't go to teachers.
I don't remember.
We did this today. The complex spectral theorem for normal.
Yes. Okay, you did complex spectral theorem.
No, I don't remember what's the spectral theorem for. I remember
Where
all
are
the
the people
theorems.
in
I
my
remember the
reading
names
group?
associated. But I don't remember the names associated with every theorem. I just know just a whole bunch of like symbols.
This
It's
week.
the big
Okay,
song.
guys.
The one where every
Stop. Spectral theorem is the one theorem that you need to know from 247 for physics, right? And you don't even need to know how to prove it. You just need to know the statement.
Wait.
The statement is, if A is self-adjoint,
We definitely have not gone over it.
okay, that implies that there exists a basis, an orthonormal basis,
of eigenvalues.
uh, basis of eigenvectors. Of A. Okay?
Mm.
This was the statement. And we proved it in like the third meeting.
Yeah.
Okay.
Question
Yes.
for clarity. It doesn't necessarily need to be self-adjoint. It can just be adjoint. Or no wait.
What would that mean?
What does that mean?
No,
What
in
would
normal.
that mean, bro?
No, it could be.
Or it can be normal, meaning that
okay.
it commutes with its adjoint.
Yes.
But
wait.
we for us we just proved it for the self-adjoint case. It's just a little simpler. It's not much simpler, but you know, I wanted to
Okay.
minimize the amount of things that are said
Okay.
at any point in time. Clearly, I was wrong because I forgot to account for the fact that if people don't show up, then everything has to be said 5 times. Okay, I was just hoping that if people do show up, I'll just have to say 3 times. Anyways, right. Good.
I understand everything. I'm locked in.
I get
Okay,
it. Thank you so
thank
much
you.
for explaining.
Good. So, And maybe, for 247's sake, you should go back and
Yeah.
rewatch the video by Elisher, because it was a pretty good discussion. Anyway, if I have a physical measurement, there is associated to it some kind of self-adjoint operator. Okay, good. The eigenvalues of this operator tell me what could possibly be measured. Okay, in general, for this kind of measurement. Okay, and then I say, okay, if I wanted to, suppose I was in this state, what could I possibly measure about my system? Well, that is given by the inner product space structure, right? Remember, we had a Hilbert space, so it has an inner product space structure. And it turns out that in a quantum mechanical system, all you can ever learn about what could possibly happen are the probabilities of outcomes, right? You can figure out what all the outcomes are. If you know the operator, you can, in principle, figure out what all the outcomes are. And then you can, if you know the state your system is currently in, you can then figure out the probabilities of you measuring this outcome, or this outcome, right?
Question. Probabilities of you measuring. Not the
Yes.
probabilities of you just knowing what might happen.
What's, okay,
there
what
like
do
a
you mean?
difference there?
What's the difference?
Like, given a system, could I know
Yes.
what might happen next, even if I do the measurement?
What do you
Wait,
mean,
when
even if you do
measure,
the
you've
measurement?
seen what's happened, bro.
I'm like
Okay.
specifying too much on wording.
So-
Sorry.
No, I mean, I think there is a good question in there. I just don't quite see it. But the point is, if you know the state of a system, then you can figure out what the probabilities of what could be measured are. Okay, you can figure out what the probabilities are of what you can measure. And that is, okay, that's very good. Yeah, and this is important. In some cases, you can have probabilities being 1, and then the probabilities of every other measurement are 0. And then, sure, you can know, for certain that I will measure this thing and not another thing. But this is the big thing about quantum mechanics, is that it really doesn't tell you, what will necessarily happen. It only tells you, some probability of what could happen. Okay? Good. And then you say, okay, suppose I do measure something, like in real life, I do an experiment, and then I have some device, and then the dial moves to, a specific number, right? And I measure this specific number. Then you have to say, well, if I measured this specific number, then if I was to instantaneously do another measurement again, surely I should get the same outcome again, right? Because I already measured it. Right?
Yeah,
So
exactly.
the state will collapse to the subspace of only thing associated to the thing you just measured,
Specific eigenvalue.
right? To the specific eigenvalue that you just measured,
That's confirmation
Okay.
bias.
right? In some sense, yes. Like if I measured this, then if I was to measure it immediately again, I should get the same thing. Like that intuitively kind of makes sense why that is the rule. And so I just do a I just do a projection onto the subspace of vectors with eigenvalue lambda. Because remember that if V is in the eigensubspace with eigenvalue lambda, then the projection onto the subspace will send V to what? Yeah, to V to itself, right? Because and this is like I have a vector along the E1 direction, and then I project it back along the E1 direction. I get the same vector, right? Okay. Once again, this whole projector business, there's a lot more to be said about projecting onto a subspace, because you really need to. That really this whole thing of projecting onto a subspace really depends on the inner product space structure. Like, you define this in terms of the inner product, but if you have an orthonormal basis of eigenvectors, you can just think of it, I had some linear combination of vectors, the ones that are in the subspace I keep, the ones that aren't I just remove them from my linear combination. Okay, that's, if you were to write things out in coordinates, you then need to show that this is independent of basis, but choice of basis, but okay. Whatever. Well, I actually do care, but for now, let's ignore the subtlety. Okay, good. Yeah, and so why was I saying this? That after you project it, right, then the probability will always be 1, because this is now a normalized, this new state is normalized, right, because I divided it by its own length. Very good. And so then if I was to apply this to this, I just get itself back, and then I'd get an eigenvalue, well, probability of 1 to measure lambda, and 0 to measure everything else. Okay. Degree, so, right. So we kind of see that, new features of quantum mechanics is this probability thing. You only know probabilities of things, that's 1. And 2, you have this is all now defined in terms of this Hilbert space structure, right? Where the inner product space, the inner product is the thing that kind of tells you the stuff about probabilities. Right? Okay, you first.
On C, we sapped everything to know where one thing could happen almost for sure.
Sorry, say that again?
Instead of having this entire system, we make everything 0 and then we make one thing 1. And that way
so
we know.
we make the components of this vector, right? So
do these vectors represent different outcomes?
these vectors, well, yes and no. These vectors are eigenvectors associated, are eigenvectors of A, right? So the eigenvector has an eigenvalue. And the eigenvalue, remember, is a possible outcome of the measurement. Do you agree?
Okay.
Right? So I only keep the eigenvectors that have the same eigenvalue as what I just measured.
Okay.
Right? So in that sense, yes. Okay.
Are all the psi vectors in the Hilbert space achievable states, or?
Ooh. This is a tough question, because usually we don't quite even know what H really is, right? Like this, the only thing we can measure in experiment are these probabilities of things, right? I can do something a bunch of times, and I can figure out what the probabilities of the outcomes are. So I can figure out what the possible eigenvalues are, or at least some of them, because what if there's my system's always in a state where one thing is incredibly unlikely, and so I never actually end up measuring a certain eigenvalue just because I prepared my state in such a way that I never see this. The only thing I can really see are eigenvalues of some self-adjoint operator. I don't even know what the operator is. And I can also maybe see the probabilities, given by this formula of the system being in some state psi, and maybe I don't even know what the state psi is. Do you agree? So the rest of, what is the Hilbert space, what is the state psi, and what is the operator A are kind of really, really clever guesswork. So, we usually don't know what this is, or what this is.
So
we kind of guess what it is, and then we see that, this guess matches pretty well for experiment. And from that perspective, I don't know, because we don't even know what this Hilbert space is. One way to think of this is, this is some theory which matches experiment pretty well. And we just we're able to figure out from lots of experiments that these should kind of be the rules. And I'm about to tell you the rules of how to figure out what A and psi are and the Hilbert spaces for a classical system. Okay, yes?
Is there a finite number of eigenvalues always?
No, you often have an infinite dimensional Hilbert space where you have an infinite number of eigenvalues, sometimes maybe even uncountable.
Okay, so you can never know every single possibility. Well,
What do you mean?
Because it's experimental, you could think you know them, but you technically never.
Well, technically you do, because at the end of the day you make a device that has a dial and it can only show the stuff on the dial, right? So from that perspective, there's something. Okay, yes. I've answered. Okay. The other thing is, right, and this is a philosophical point. We'll be here a long while, but that's okay. that this whole, measurement business, right? I say a measurement happens, right? We do a measurement, and then the state collapses in this way, right? But when we say measurement, that's always like some kind of classical operation, right? Like I look at the dial and the dial moves this way. Like that's something about classical mechanics. So there's clearly, this and this is a problem that many people have with classical mechanics, is that this thing of like this measurement process is some kind of sharp transition from like quantum mechanical world of Hilbert space to, we do something classical. The measurement is somehow classical, and then there's this sharp transition with this collapse of the, eigenstate of the state. And this is something that people, don't quite like, because, you could say, oh, but, what if I included the state of my detector into my Hilbert space, right? And then computed the probabilities of that. But then, at the end of the day, right, I would only get probabilities of what could be measured, right? I would never actually describe, what will happen. So maybe I'm not being entirely clear, but the idea is that, this kind of thing of I measure something and the wave function collapses, this is, somehow not like, the rest of the postulates, right? This is somehow different from just having some vector which evolves in some way. Okay, yes, question.
Is this why you specifically chose like probability of your measurement, not probability of the system? The measurement itself could depend on you observing or not.
So, yeah, this, not quite, well, yes. The measurement is what you as an observer, what you observe the measurement to be, right? The probability of a system, I don't know what that means, but there's probabilities of what I can see in the experiment, but once I see it, that's what I saw, and that's what the system is now, right? But this process of me seeing, right, this is very different from all of these things before, where everything before I kind of defined in terms of everything before I defined in terms of like linear operations, and this is somehow something non-linear, right? So there's a bit of a, after what point do you stop modeling the system as quantum mechanical vector in Hilbert space and say, okay, now I measure this, and this is what my, measurement is. Okay. And there's a great course, Physics 491, that you should take to have a more clear picture of what I'm trying to say. Okay, yes?
What does that H depend on, the equation?
H? This is the observable associated to energy measurement. So I didn't say this. Observable,
Hamiltonian, like what we went over.
yeah, associated to energy measurement.
It's all making sense.
Okay. Yeah, so you can measure the energy, whatever that means, and by these rules there should be some abstract self-adjoint operator associated to it, and so your evolution in time, your state will evolve in time according to this equation. This is some self-adjoint linear operator. That's all it is. Okay. And from the discussion on the one day where I just talked about random things, you now know why there's a factor of I in there, because the factor of I is just the factor of I just comes from the fact that you want to conserve probability as you evolve in time. You want to conserve these inner products as you evolve in time. And so because of that, the I has to be there. If you don't remember exactly how that follows, okay, you can go back and look at it. And what's one more thing? Yeah, okay. How to solve the Schrödinger equation, we'll talk about that later. Okay, you had a question? Okay. So now the question is, I give you all of these rules where I need to know some Hilbert space, I need to know some self-adjoint operator for associated to some measurement, I need to know the state psi, how do I do this? You know, I just gave you, you know, suppose all of these things exist. How do I actually use this to make some computation? And so there is this, there's a procedure that Schrodinger came up with, and this is like Schrodinger's wave equation. This is the whole point of how to take a classical system and quantize it. Meaning, take a classical system where you have some classical observables and figure out what the kind of Hilbert space has to be, what the self-adjoint operators have to be, and so on and so forth. Okay? So, quantization. And this is actually like a lot more subtle than what I tell you. And there's like kind of different ways that you could quantize a system, which are all kind of similar. Like there's a lot to be said about this, but I'll give you some heuristic rules, which you can usually apply in like all the simple cases. And then, you know, different people have come up with different conventions for how to have like a general scheme of quantizing things. And also, the mathematicians have studied this in quite a bit of detail and have come up with a lot of like math to make this process very rigorous. And mathematicians call, this what I'm telling you isn't what mathematicians call this, but you know, there's a mathematical way to describe this, which is much more involved, which people call geometric quantization. So geometric quantization is kind of based on this, roughly what I'm going to tell you, but it's you know, this is like more, this is something else in some sense. Okay, but this is based on this heuristic idea, right? I'm just telling you an idea. So classically, what do I have? So I'm going to describe the rules for quantizing the motion of a single particle. So I'm going to tell you the rules, motion of a single particle. Okay. So I have classically, okay. Classically, and then we have quantum mechanics. Classically, I had my particle, right, and it would so the state space, the state was some point, some pair x comma p on some manifold. Okay, on some manifold. Usually R, okay, Rn, right? So classically, I have a particle that can move around, right? Well, sorry, R to the 2n. And to describe the state of a particle, I need to tell you where it is and how fast it's moving and in which direction, roughly. Right? And so that would be described as a state in some, as some pair of numbers, x and p. Okay. Maybe x and p would be vectors if I have, you know, multi-dimensional case, but that's all right. Okay. Now in quantum mechanics, the state of a system has to be some vector in some Hilbert space. Okay. Huh? So I have to tell you what the Hilbert space is, right? So I will say it this way. So in Q, let how much time do we have? Okay. I'll try and finish in the next 30 minutes, so we're not too long. So let M be kind of the space where the particle can be configuration space. So M is all the possible positions that the particle can be at. Okay. So usually Rn in our case. Okay. Do you agree? So all I'm saying, M is just the possible positions the particle can have. And then the Hilbert space will be the set of functions going from this space to C such that if I was to integrate the absolute value squared of this function over this space, that will be some finite number. Okay. And this is often called the L2 space over M. Yes.
Integration on
Some set. So I have a set M.
Yeah.
That's where that's like where the particle can be, right? In real space, you can imagine like I have a box, let's say, right? The particle can be in some box, so then M is like R3. Or well, not R3, but like some cube.
yeah.
Okay? Then I can look at functions which take input in the cube and output a complex number.
Yeah.
Do you agree? So it's a function. I
okay,
can
okay.
I can integrate the function over
Okay.
this space.
Is
Okay.
that function f and the psi?
Oh, sorry, the psi. That should be psi. I wrote psi. So I can take this function. I can take the absolute value squared, and then I can compute the integral over the whole space where I can be. Do you agree? Very good. Okay, I'm going to erase this, and we're gonna like loop back up because I just want all of this on one book.
Bottom part, no, please.
No, I'm gonna only erase the top part. Don't worry. Okay. And now I'm going to tell you. So I told you what the states are. Do you agree? So we've dealt with postulate 1, right? I've told you what the states are. I've told you what the Hilbert space is. Now I need to just tell you how to figure out what the observable is. Do you agree? Okay. And so now we figured out in the following way. So now, remember, classically, what is an observable classically? What is an observable classically? Yes.
What can you observe?
I guess
Not a point.
energy or something.
Velocity?
No, yeah, but okay. If to tell you, so suppose I have a classical system, right? So I have some particle moving along some path, right? And this path is going to be in this XP space, right? The path is at every point. I need to at every point in time. I need to specify the position and the momentum of the particle. Okay. So suppose a particle has some position and some momentum, right? How do I, if I wanted to calculate the energy, right? I have some expression for the energy,
Yeah.
and how do I calculate the energy? I plug in what?
Velocity.
The position and the velocity of and the momentum of my particle, right?
Okay, yeah.
So this means the observable is what? It's something that takes in
The position and momentum.
momentum and outputs
A scalar.
a scalar. So therefore, it is a function. Observable, A, is some function of x and p, which gives me a real number. Do you agree? So it takes what my state is. It takes in what my state is and outputs a number. Do you agree? Now this is the tricky part. What do I do quantum mechanically?
Give up.
Okay, quantum mechanically, what I get in the end has to be some self-adjoint operator.
Yeah.
So how are we going to do this? So hopefully this a of x and p is something that I can I have some expression that I can write in terms of x and p. Do you agree? So I do this formally, and this is where the ambiguity comes in, and then, but we won't deal with it. So formally, I write a of x comma p, right? I just write down the same expression, but instead of x, I write multiplication by x, and instead of p, I write minus I h bar partial x. Okay? And then I just, everywhere in this expression, I replace x with this operator, m of x, where what does it do? M of x is going to be an operator which takes a wave function psi of x and returns another wave function x psi of x. Okay? And this is also some operator which takes a wave function, so p of psi is going to just return minus I h bar the derivative of psi. Okay.
So that's just multiplication.
Yeah, this is the multiplication operator. It takes a function, multiplies it by x. Right? So see, this is still an operator. It takes in a function, it outputs a function. And these are operators almost on this L2 space, but okay, let's, for now, just don't worry about it. These are operators on the L2 space. Yes?
Is there a reason for its similarity to the Schrodinger equation?
Hmm?
If you look on the left term, is then that's just momentum, but you're not taking partial time.
I would,
Both of them just multiply.
no, not this one multiplies by x.
Yeah.
This one takes a derivative of the function.
Oh, that's why. Oh,
This is partial x.
Aye.
Do you agree?
Mm-hmm.
This is not multiplication.
That's also m, not mu.
This is like curly cursive capital
Yeah.
M.
So this is that's like, yeah, okay. So that's like.
So this is multiplication by x. This is the operation of taking a function and returning the function multiplied by x. Do you agree? This is an operator, this is an operator. Do you agree? And what you do formally is you have this function, which is some expression of x and p. Do you agree? And everywhere where you have x, you replace that with this multiplication operator. Everywhere you have p, you replace it with this differential operator. And now you have some expression,
Yeah.
which is written as some composition of operators.
Yeah.
And you should get back, okay, and then you now get this a of xp now becomes some operator, okay? And so we took this classical thing and turned it into the hopefully self-adjoint operator, okay? Do you agree?
Yeah.
Okay, for the case of a of as a function of x and p, there's a lot of ambiguities, especially classically, it doesn't matter if you write x times p or p times x, versus quantum mechanically, if you take a derivative first and then multiply by x, versus you multiply by x first and then take a derivative, there's a difference. So there's that ambiguity, like it already matters like how you write this, you might get different results for how you quantize. And there's a lot of details about how to do this properly. And so there's certain schemes which give you like some generic way to do it. There's certain schemes where people just know like, oh, in this case I should do this, and in that case I should do that. But we actually won't worry about this too much. We'll primarily be looking at stuff that is either only depends on p or only depends on x. And okay, when it will matter, we'll figure it out. Okay, yes.
So like, for example, if like this was like a string, and we were looking at energy as the linear operator.
Yes.
Right? You have the potential based on its x, and then the
Yes.
momentum to give its kinetic, and then when you make it here, you just replace wherever there's an x with x times the
With the operation of multiplying by x squared.
x squared.
Well, because you'll have kx
okay,
squared
yeah.
over 2, right?
And
And so, yes.
And the kinetic one will be swapped with the
Yes.
derivative in terms of
Yes.
x. Okay.
That's right. So let's do finally an example, right? So now I've told you everything that you need to know to be able to start trying to do something yourself with, a single particle moving around in some space. Okay? Do you agree? So I told you, what the rules are, and then I told you how to go from a classical system to a quantum mechanical system, how to figure out what the Hilbert space is, what the states are, and what the observables are from the classical thing. Okay? And Schrodinger is the first person to have figured this out. Well, I guess. Yeah, I think he was the first person to have figured this out, and he wrote this down, and he wrote the Schrodinger equation, and that was figuring out that this is the thing you have to do is clearly a massive achievement. This is not obvious, at all. Okay, in hindsight, to a mathematician, it might now be obvious. The people who study geometric quantization, they're like, oh, of course, this is the natural Hilbert space that arises if you have this, symplectic manifold. This is, of course, the first thing you try, but I don't think people knew about symplectic manifolds back then, and most definitely the physicists didn't know about symplectic manifolds. And I think the physicists didn't even know about linear algebra, because when Dirac came up with it was Dirac, right? Or Heisenberg. No, Heisenberg came up with matrix mechanics, right? He came up with matrix mechanics, and he was starting to, he realized oh, if I want to, compute the possible outcomes, then I should multiply things in such and such a way, okay? And he realized this, and then he showed this to a supervisor, and his supervisor is like, why are you computing things in this way? Mathematicians know this. This is just, these are matrices, and you're just doing linear operations. And he was like, oh, okay. And then he had to have his supervisor explain to him what linear algebra was. But also, partially because modern linear algebra was phrased in this nice way with matrices and everything. Actually, only also in maybe late 1800s, early 1900s. I'm not so sure, but all of these things are deeply not obvious if you don't know the answer. But if you know the answer, it's very easy. Okay, and so you know the answer. So let's look at a simplest case. Do people prefer if I keep writing on this side or on this side? Okay, the people on makes sense. Is there a second board? No, that's the second board. Very good. Okay, so let's write here. Example, finally. Let's go. Example is particle in a box. And this is precisely, this was the tutorial bonus question from a while ago, from Math 240. Right? I've already discussed this example in my office hour. If you didn't come to office hour, what can I say?
Unfortunate.
Great. And I kind of listed these rules in office hour as well, but I didn't, we didn't know what an inner product space was. We didn't know what anything was. Good. Example, particle in a box. So, sorry, I forgot to say, one-dimensional particle in a one-dimensional box. To make life easier. Okay. So, first of all, we got to follow these rules, right? We got to follow these rules, and we just have to apply these rules. So one, what's the so suppose particle. Particle is restricted to be in a box to be in box to be from 0 to L. Okay? Do you agree? So it's I have some some 0 to L, and the particle can only be somewhere in here. Okay? Good. This is precisely what in here? Out of the stuff written here, which letter is this interval 0 to L?
X.
No. 0 to L is what x can be, the values x can take on.
Yeah.
But what's the space 0 to L?
M?
M,
No,
yes.
yeah.
So the space where the particle can be is 0 to L. So this means what? That the Hilbert space is,
All functions from 0 to L.
Yes, all the functions from 0 to L to C, which do what? Such that if I integrate them from 0 to L, and I integrate the magnitude squared dx, I'll get some finite value. Okay. Oh, whoops, sorry. I completely forgot to tell you the most important thing. I forgot to tell you what the inner product on my Hilbert space is.
Not the dot product.
Well, it's a function. How do you dot
Right.
product? Sorry. So I'll kind of add this over here. The inner product is the dot product. The inner product between two functions is going to be the integral over m of f of x times g bar of x dx. So almost the dot product. Do you agree? It's just that now I kind of
Yeah.
have infinitely many directions, and I integrate over them. Yes.
Just to make sure, are we putting the conjugate on G and not F?
We're gonna put the conjugate on G, but at some point we might put it on F. Remember, this is the mathematician's notation. The physicist's notation is to put the conjugate on F. Right? So this is the mathematician convention.
Yeah, yeah.
Physicists define the inner product to be linear in the second entry, not the first entry. So whenever you read a quantum mechanics textbook
That's why.
written by a physicist, it's always the other convention. Okay, whenever you read a book on like linear operators in linear algebra, it's always the other convention. Okay, and I'll get confused. I will use the wrong convention and I'll get the right answer. But the whatever is in between might be a little off by everything. But the answer will hopefully be correct. Up to every factor. So up to it being wrong, it will be correct. Good. So this is the Hilbert space. All the functions that are, a square integrable. Good. On the unit interval. Now, let's look at what, we have to figure out, what are some possible observables. Right? Let's look at the, most important observable, the one that appears in the Schrodinger equation, right? The observable associated to energy measurement. Okay? So I have to tell you, what is the energy classically? Do people know what the energy classically is for a particle, free particle? What is the energy of a free particle? P squared over 2m, right? That's right. Do you agree?
Yeah.
P squared over 2m, you can think of it 1/2 mv squared
Yeah.
over 2, but then p is mv, and so you rewrite it as p squared over 2m. Good. But now I said that my particle is restricted to be in a box. Do you agree? So I can actually write this plus v of x, where v of x is, okay, this is like formally, this is not real. What I'm telling you is kind of like once again, an intuitive thing to say, but the function is 0 if x is in 0 to L, and then it's infinite if x is not in 0 to L.
Cool.
Do you agree? So roughly, there is no energy cost for me to be inside the box, and there is an infinite amount of energy that I need to
So it
put in
can't
to
be
be
the box.
outside of the box. So essentially, I can't be outside of the box.
Okay.
That's the idea. Okay. And so now, how does this become? What does this become in the quantum theory? Can I measure infinite momentum? No, so it doesn't happen, as far as I'm concerned. Remember, every observable associated to a measurement, associated to a dial turning to some value. Therefore,
It's like exponential. Can never reach the end. It
Yeah.
touches the end.
no, but also your dial is, okay, whatever.
It's like a logarithmic dial.
Good. So now let's apply the rules, right? I have some expression for p and v of x. Do you agree?
Yeah.
So let's rewrite it according to this rule. So I have to replace p with minus I h bar partial x. Do you agree? And also I have this thing, I have an operator squared, but I can interpret that as I compose the operator with itself, right? So I just do p and then I apply p again. So then, if I apply p and p again, this means I do minus ih bar, I take a derivative, and then I do minus ih bar again, and I take a derivative. The minuses cancel out. The i's, I get an I squared.
Negative 1.
I get minus h bar squared. That's a constant I can
Wait,
take
you
a
show
note.
every step
Okay.
per chance?
That's no, I mean, honestly, that's a valid thing. Valid request. Okay, do you agree? Plus multiplication by v of x. Do you agree? Like v of x is some function that depends on x. So I can just according to this rule, right? Anything like x turns into multiplication by x. So some function v of x should turn into multiplication by this function v of x. Do you agree? Okay. Okay, but now I'm just composing two derivatives. This is a linear operator which acts on functions by taking the derivative. So if I take a derivative of a function multiplied by some constant, then I take another derivative of a function multiplied by some constant, I can factor out the constants. Do you agree? So it's minus ih bar squared. That will give me what? That will give me
Negative 1.
minus h squared.
Oh, shit.
Do you agree? Because minuses cancel out. The i's give me a minus. Okay, and then I just have to take a derivative squared over 2m. Okay. And then the other thing is, I realize, wait a second. I want to get finite energies. Do you agree? So I will restrict myself to wave functions. Actually, wait, sorry. I don't want to be at the walls either. So I'm going to do this kind of condition. Sorry. I'm gonna, if x is not like within the interior of the box, then it's 0. If it's on the boundary or the exterior of the box, it's infinite. So then, I'm going to make the following restriction on my Hilbert space. If I want finite energies, this thing multiplies my function by something infinite, right? That clearly could give me some infinite eigenvalue. Also, like, what does this even mean? I don't want to even deal with what this means. So I'm going to make a restriction. I'm going to make my Hilbert space. So I'll add the restriction here, but you write it, again. I'll make the restriction that also psi of 0 equals psi of L equals 0. Do you agree? So I make the wave function be 0 at the ends. Do you agree? Yes.
Does it mean it has no energy at the ends?
That's not quite what that means. No. Because remember, the energy is something p squared. The energy is something about the derivative. Do you agree? So it would be something about the derivative at the ends, and the derivative can be whatever. I just want the value of the function to be the same. Okay. Do you agree? And so this is going to be, now that I have this additional restriction, this will always be multiplication by 0, and so that's just 0. Okay, so my Hamiltonian is minus h by squared partial x squared over 2m. Do you agree? Okay. Do you agree? Good. So now, now we've done our rules. We figured out what the Hilbert space is. We figured out what one of the observables is. Do you agree? And now, suppose I wanted to compute what the allowed energies are. Okay? Suppose I wanted to compute what the allowed energies are. How do I figure out what the allowed energies are?
The range.
Hmm?
The range.
The possible energies. I compute the eigenvalues of what?
Yeah.
Of this operator
Yeah.
on this set of functions.
Yeah.
Do you agree? So,
Oh.
and we've done this in the office hours. Do you agree? And I got like everything wrong, and I will get it wrong again. But okay, we'll just kind of quickly do this and look at an example or two. Okay, but and the surprising thing is this looks like literally the simplest model you could possibly ever do. Do you agree?
Yeah.
And it is, because it is. This is like literally a free particle restricted to some
Like
space.
they're not even moving with that simpler.
I guess that would be simpler, but so actually, I did read in fourth year. I took this course, and we had to read a paper, like for a final project, to read a paper and write about this paper and try and summarize the thing. And there was this paper from the 60s. It was very interesting, and it was they were studying this 0 + 1 dimensional quantum field theory. What does this mean? This means that you have a particle sitting in a single point, and it just evolves in time. And that was actually an incredibly complicated system. Does not describe reality in any way at all, but very interesting mathematically. Okay, you had a question. No, okay, you had a question.
That's the Hilbert space, the one in red.
This is H, the Hilbert space. This is straight H, the linear operator associated to energy, also called the Hamiltonian.
Oh.
Hamiltonian. So this should be stated.
Wait, hold on. Okay.
So this simplest system, despite being the simplest system possible, I have been told, I've not actually had time to prepare and talk about this myself, but apparently this actually describes quantum dots.
What is that?
I think the idea with quantum dots is you have like an electron, and then you find a way to confine it in a very small space. So quite literally, you take a particle and put it in a small box.
Okay.
And then what's useful is that can like this electron can emit light. Do you agree?
Mhm.
But it can only emit light of like the appropriate energies, as we will see in a second. And we're about to compute what the energies are in a moment. And so in principle, the kind of dispersion of energies, how their energy levels, how they're distributed, is well described by this very, very, very simple model for these quantum dots. Okay, how you manufacture these quantum dots, everything, I don't know. I have not read about this, but this actually has some relation to reality, unlike the 0 + 1 dimensional quantum field theory. That has, I don't think that has any relation to reality. Okay. So now, let's quickly compute the eigenvalues, make a few comments, and then leave, and then you'll finish the rest next time. I also have to write you're stressed that you have to, do stuff. I'm stressed because I actually have to write the readings for you and, make a point and, okay. Should I write things here or there? Let's write things. Let's write things here. So I want to compute the eigenvalues of so energies will be eigenvalues of H. So I want to compute the eigenvalues of H. So I want to solve the eigenvalue problem, right? I want to find E's, I want to find states psi, and states H such that H of psi is equal to what? Is equal to? E, let's do E of psi. E for energy. Do you agree? So I want to solve this equation. I want to find numbers that do this. Okay? So, okay, I just write it down and I get an equation. We make the very nice simplifying assumption that what? That, of course, actually, okay, I want to say that, H bar is equal to 1, M is equal to 1/2, but okay, you know what? We won't do it. I am stronger than this. I can maybe solve this. Okay, so I get, the equation is what? Minus H bar squared over 2m. I take the second derivative of psi, and this has to be equal to E of psi. Do you agree? Does this look at all familiar to people?
I,
Wait, can we not just
that?
put the eigenvalue
No,
the same
wait,
way that we
2m.
did 240
Well, what do you mean?
with like the a minus lambda I?
I mean, that's what I did. That's what I wrote down, right? I wrote down the a minus lambda I equals 0 equation.
Oh, okay.
I just,
You just wrote it on the other side.
yeah, that's it. That's what we're doing.
Okay.
But okay, so let me, this is a constant, I can multiply it on the other side. I get partial x squared phi is equal to minus e over h bar squared, and there's a 2m in here. Side, do you agree? Okay. Also, yeah,
Is it something like, let's say, quadratic?
the side,
I mean, yes, eventually.
the energies are quadratic, will be quadratic in some sense. Psi, no. So, okay, look, we have a simple differential equation. Every physics person in the room should know how to solve this
oof.
immediately. Like, you should look at this and immediately tell me what the answer kind of looks like.
E or sine or cosine.
Sine and cosine is a good answer. So,
Okay.
what you should have ingrained.
Second derivative, right?
Yes, it's the
Yeah.
second derivative. So if it was first, so you should have ingrained in your memory two facts. The two facts should be what? That if you have some differential equation, f dot is equal to lambda f, then the solution is constant times e to the lambda t. Do you agree? Suppose these are functions of t. And if you had f double dot of t is equal to lambda squared f, then the solution is a sine lambda t plus b cosine lambda t.
Ah.
Okay?
Physics just made a lot more sense.
Right? The harmonic
Harmonic,
oscillator
yeah,
is your,
yeah.
in the harmonic, when you solve the classical harmonic
Yeah.
oscillator, you're literally just solving this equation. Right? And this is what we also did in office hour. Okay? You know, everything so far we've done, nothing today that I haven't talked about in office hour. We're still in the realm of that office hour. And we will be for, the next 5 minutes. Okay, do you agree? So using this fact, we know that the solution psi has to be what? Some a times sine of e m over h bar, but then I want to take a square root of this. X. 2, what 2? Yeah, there's a 2. Plus b cosine of the same square root 2em over h bar squared x. Okay. And so last time, I think, when I did this in office hour, I messed up. My 2e over m was at the bottom and h bar squared was at the top. Because I don't know, I just messed up. Okay, do you agree? But now, we can say a lot more. Right? Because remember, with this assumption that my particle shouldn't leak out of the box, because that should cost infinite energy in some sense, I assumed that at x equals 0 and at x equals L, my function should be 0. Do you agree?
Yeah.
So this means, so I plug in 0,
Yeah.
right? This is a function of x.
Only you can get
I plug in 0, and this term is what? This term is?
0.
But this term is b. So clearly b has to be?
Non-zero.
No,
No,
b has
yes.
to be 0. Yes. So, due to boundary conditions, b has to be 0. Okay. But this is, I used the condition at 0. Do you agree? Now I have to use the condition at L. Do you agree? So let's try, psi at L. Yeah,
Yes.
you most
We did.
definitely did this in
It was
one
homework
lesson.
for reading week that I did
Yes.
do.
Sorry, and doesn't it depend on square root of 2em over h to the power of 2?
What the?
Oh, sorry, no, I think.
Yes. So, if I plug in x equals 0, this goes to 0. This also goes to 0 because it's just 0, and so this is 1, so it's b, but b 0. And now we're going to get some restriction on what e can be from the second condition. From the second condition, I get that a sine square root 2em over h bar squared times L has to also be 0. Agree? Always has to be 0. Agree? Because I don't want my particle to leak out of the box.
So what happened to B there?
V0.
B was set
Oh,
to
B
0
is
because
0.
at x equals 0 I want this to be 0,
Yeah,
so
yeah.
B has to be
Wait.
2 EM over.
0. 2 root 2 e times m over
Okay.
h bar squared.
I thought there was like vector E or something. Thank you.
Okay? Agree? Okay, but for sine of something to be 0, this something has to be a what? Times L has to be equal to some n times pi. Do you agree? Some integer multiple, where n is, let's say, a positive integer. So say a natural number union 0. Okay? Do you agree? So this whole thing can only be some particular number. But wait a second. H bar is some constant that is, we know what it is. L is the size of my box, I can measure that. M is the mass of electron I look up in the table. So the only thing that could, this is really only a condition on the possible energies. Do you agree? So let's solve for the energies. The energies should now be n pi over L. Let me just write it. Pi squared, h bar squared pi squared over 2m L squared times n squared. Can someone check if this is correct? Oh, yeah, I have the, yeah, that's right. Do you agree?
Yeah.
Okay. Now note that these e's, right? This is a constant. Agree? This is some constant that's determined by what kind of system I have. The size of the box, the mass of the electron, all these things. This is some fixed constant. Agree? But n is some arbitrary natural number that I can kind of choose. Do you agree with this?
Yes.
Therefore, I see that my allowed energies are restricted. They're only allowed to be multiples of the integers squared. Therefore, we immediately see that energy is quantized. Okay. Why was the energy quantized? Can someone tell me? Why did we get this energy is quantized? What was the key assumption that we made? Yes.
A is non-zero.
Well, A is non-zero, but before that. Before that, what was the, Sure, A is non-zero, but where did I get this equation from?
Boundary conditions?
Boundary conditions. And why, physically, what did the boundary conditions mean?
That you escape energy.
That the particle can't escape from the box. Do you agree? So, right, we got this. We tried to restrict our particle to some finite region. And because of that, I got some boundary conditions. And because of the boundary conditions, I got that the energy is quantized. And this is, I'll get you in a second. And this is actually something that is kind of generic actually, like very often when you try and like restrict something to a finite space, the energy ends up being quantized because of boundary condition. Not always. You know, you actually have to write down the Hamiltonian, diagonalize it, find the eigenvalues, and figure out what can and can't happen. But in this particular case, you know, you got quantum. Now, the big thing is, you know, it's called quantum mechanics, right? You know, from these postulates, you can see there is nothing that is said about anything being quantized, right? It is not necessarily true that your eigenvalues have to be discrete. It's just that the first time that they studied like a system where quantum mechanics played a big role, well, not the first time, but the first time they, you know, really saw something might be going on, they realized that the energies are quantized, and that's, you know, the first thing that they realized. And so they called it quantum mechanics eventually after, because that was one of the first effects that you saw. But in principle, you could have some continuous spectrum of eigenvalues, in principle. Okay, question.
What if we said x could be at the boundary? So x not included in the open bracket 0 to L.
Well, then you'd have that you can have, you know, kind of any energies, but then that wouldn't quite physically make sense because, okay, as we'll see much later, or maybe we won't see this semester, but this would mean that there's some probability that the particle could kind of be very, very close to the like on the boundary essentially, but that doesn't make sense because that means it's like in the wall of the box. So like just on physical grounds, this is what should happen, and you get quantization of energy. Okay, good.
Okay, thank you.
And so then I can figure out, I can then write down what my eigenfunctions have to be. And I can now, I know that energy has to be, every energy is associated to some integer. So I can now index everything by this integer. Do you agree? Is going to be, so some constant a, sine of, okay, now I just have to plug this into, you know, root 2 e m over h bar. So I plug this into here, the 2's cancel out, the m's cancel out, the h bar squares cancel out, so I'm just left with n pi over L x.
So what about the L on the outside?
Where?
Yeah, that one.
That was because I plugged in instead of x,
Oh,
I
okay,
plugged in
yeah.
L. Okay. Do you agree? And now remember, so, what, another thing I forgot to mention is that here the state is in state psi, where the norm of psi is 1. So, and then we normalize states. This probability equation is written for normalized states.
Yeah.
Okay. So if I want to have a normalized state, then A should be what? It should be 1 over the norm of the function. Do you agree? So what is that? What is the norm of this function? Sorry, what is the, how would I normalize this?
Dot product.
Yeah, dot product of what with it? I take sine, this sine np over Lx, inner product sine np over Lx. Do you agree? But what is this? How do I, oh, sorry. I want, and then I want to square root that. Yeah, okay. And what is this expression, this inner product? That's the integral of?
Yeah, multiply. One's like
Of
yeah.
sine and pi over Lx squared. So it's 1 over square root integral sine n cubed over Lx all squared.
Evaluated from 0 to L.
From 0 to L, that's right.
Okay.
Good. Okay. Kind of out of space.
Oh, but it's
So
This
beautiful.
side
This is a beautiful board, but I don't want to erase anything. This is so beautiful.
I know, it's so
There's
comfortable.
there's space in the
right.
back.
Okay, there's space exactly here.
No, Ivan, you can.
Two more boards.
No, but I don't. I want to have everything be visible.
Ah.
I don't want to.
There's 2 more boards here.
Oh, great idea. Beautiful. Okay. I mean, people people do use these boards in lecture all the time, so.
Boards are clean as well.
Okay, yeah, because no one uses them. Good. So now some final comment. So far we've only computed the energy. So a few things that we didn't check. We should have checked these, but we didn't. So remember, observables are supposed to be what kind of operators? Self-adjoint. Okay. So we should check. You know, is H self-adjoint? Okay. And actually, it is self-adjoint, but the boundary conditions are very important for it being self-adjoint, because you're going to do some integration by parts, and you want stuff at the boundaries to go to 0. Okay, whatever. But the other thing is, you know, I have P. I defined these operators P and X, right? P was this taking a derivative. X was multiplying by X. Do you agree? And position and momentum, those also should be something I can measure. I should be able to measure the momentum of the particle, the position of the particle. Do you agree?
Yep.
So the question is, are, you know, P and kind of multiplication by X self-adjoint? You know, that's also something you should check. Okay? These are essentially like homework problems for you. You know, check that H is self-adjoint, check that P and X are self-adjoint on this Hilbert space with this inner product. Okay? I mean, these are trivial exercises, but it's maybe non-trivial the first time you see it. They're good. They're good to do. To write it out. It's like one line, each of these statements. And now the final thing is, remember. So, remember that self-adjoint operator should have a basis of eigenvectors, orthonormal basis of eigenvectors. Do you agree? So this means, and I think we checked before, that if two eigenvectors of the same operator have different eigenvalues, then they necessarily have to be orthogonal. Do you agree? Do people remember what orthogonal means?
Yeah.
It means?
One dot other is equal to 0.
Yes, inner product is 0. Do you agree? I have these beautiful eigenvectors. Do you agree? Of some self-adjoint operator. Do you agree? So they, in some sense, should be they should be orthogonal to each other for different n.
Yeah.
That's the first thing. And the other fun thing is, wait a second. Didn't we say that this should form a basis?
Yeah.
Okay.
It's very big. It
So-
doesn't matter what basis you
Yes.
pick.
So from physics, you know, from this kind of thing that we did, we now realized, wait a second. Any square integrable function any square integrable function from 0 to L, I should be able to write it as some linear combination of signs. Do you agree? That goes to 0 at 0 and L. I should be able to write it as some linear combination of signs. This is actually essentially the Fourier series. Right? The idea behind the Fourier series is completely trivial. It just says that something is an orthonormal basis, and you can write it in that basis. And that's all it is. Do you agree? And so this is kind of the non-trivial statement that sine of np over Lx, inner product sine of m pi over Lx, this should be delta function of n and m. So if they're equal, it's 1. If they're not equal, it's 0. And actually, there should be some normalization factor of, like, let's say L or L over 2, maybe I think L over 2, something like this. L over 2 because, you know, sine itself is not normalized, so there's some factor floating around. But yeah, these form an orthogonal basis, not normal. You can normalize them, but no one cares. Okay? And so, I mean, this is like a purely math statement, right? This has nothing to do with physics. If you show that this linear operator, this is a linear operator, is self-adjoint on this vector space, then you should and you found the eigenfunctions, the eigenvectors, then you should expect that that this should form a basis, and you should be able to write any function as a linear, potentially infinite linear combination of these vectors. Now, that actually, you'd need to say a lot more words, because really, we proved the spectral theorem only in finite dimensions, and here's some infinite dimensional space, right? In fact, someone was asking, do you always have finitely many eigenvalues? No. Here's an example where I have infinitely many eigenvalues, countably many, as many as there are integers. Okay, yes?
Kronecker delta.
Yeah, Kronecker delta, so delta and m, what this means is 1
And
if n is equal to m, 0
Not
else.
once.
It's just a symbol so that I don't have to write, you know, this. Okay. Do people have some sense of what's going on? Yes?
No, sorry, I forgot that.
That's okay. So, one thing that I think Archit might talk about, or maybe not, I've still not decided. But you know, we computed the energy. The next thing you might try to do is like, okay, what are the possible x values and what are the possible, measurements of momentum? Do you agree? And then you try and find the eigenvectors of this, and then you try and find the eigenvectors of this, and you realize that kind of not so easy, right? And for x, it's actually not too bad. For x, we can invent something called a delta function and pretend that that makes sense and be happy. But for p, there's clearly, something that's going on. You won't be able to find eigenvectors of p for some reason. It will be, strange. Have people heard of and if I tell you this now, I'll spoil too much, and then Archit will not have this like, wow, this is so cool moment in what he's doing. But this p thing, you'll realize there are no eigenvectors, and this will be roughly related to the Heisenberg uncertainty principle. Like there'll be, you can compute and show that there's, that you can't get something, but you will be able to, but you'll have some like simple physical picture to explain. Okay.
Yes.
We're done. Let's stop here.
So
Archit will present next